Alright guys, today we're going to be talking about parametric equations. And parametric equations are essentially a pair of equations where x is dependent upon time and y is dependent upon time. And so essentially there are three variables. There's time, there's x, and then there's y. And the way this works is that the time variable is actually not graphed, but it controls the direction that this object is moving. So, for instance, let's say we set up a table, and in this table we are going to have three columns. So time and x and y. And so we'll pick some random values for time, maybe 1 second, 2 seconds, and 5 seconds, and that should be enough. So you're going to plug your time value, t, into both the x and the y equation. So when time is 1, the x is going to be the square root of 1 minus 1, which is 0, and so that's just going to be 0. And then the y equation is going to be 1 plus 2, because this is the equation for y. And so 1 plus 2, that's going to give us 3. And so the object starts at 0, 3. So when the clock starts at time 1, should I say, that is where the object is. Alright, so now when time is 2, the x is going to be 1 and the y is going to be 4. And you can see where this is going when t is 5. Now you say, well, why did I jump from skip over 3 and 4? Well, you want to pick numbers that you can easily take the square root of here. And so I picked 5 because 5 minus 1 gives us 4, and the square root of 4 is 2. And so this is going to be 2 and 7. And so the object goes over 1 up 4, and then over 2, and looks like up 7, somewhere up here. And so the object is moving in this direction. All right. And so the next thing they want us to do is actually figure out what is the real equation of this particular graph. And essentially with parametrics, if you remember from pre-cal, it enables you to sketch part of graphs. This is how we did the calculator project in pre-cal last year. When you only wanted a certain portion of the graph, you can control how much of that graph you want by controlling the time that you let this thing run. So we are going to figure out what equation this is by eliminating the parameter, which essentially means you're going to solve both equations for t and set them equal to each other so that the letter t is eliminated. So let's start with x equals the square root of t minus 1, and we will have y equals t plus 2. So I'm going to square both sides here, and you get x squared is equal to t minus 1. And over here in the green, we are going to get y minus 2 equals t. And over here in the red, we're going to get x squared plus 1 equals t. Well, y minus 2 equals t, and x squared plus 1 equals t. So therefore, we can set these two things equal to each other. And that's going to end up giving us x squared plus 1 equals y minus 2. And you add 2 to both sides, and x squared plus 3 equals y. And that is the equation. And you can see that this particular equation looks like a parabola shifted up 3 units. Okay, in this second example, we have two trig functions, and we want to do the similar thing that we did in example 1. And so we're going to make a table, and in this table, once again, in one column we're going to put t, in the next column we're going to put x, and then y. And for these trig functions, the best thing to do is really just to pick angles, the most basic angles that you can quickly figure out what the sine and cosine values are. So we're going to pick all the angles that are on either the x or the y axis. And so that's going to be 0, pi over 2, pi, 3 pi over 2, and 2 pi. All right, and we're just going to plug all those things in for t into both of these equations. So to save time, I know you can do this. I'm just going to give you these values, and so you get 5, 3, 1, 3, and 5 for the x's. All right, and then for the y's, you're going to have -1, 2, -1, -4, and -1. And so if we want to graph this, we can see that the object, whatever that object is, it is starting out at the point 5, -1, and then it's moving to 3, 2, and then 1, -1, and then 3, -4, and then back. So the object essentially starts here and goes in the shape of, well, it looks like an ellipse, but we need to prove that, and so we're going to eliminate the parameter. So for the x equation, we're going to subtract 3 from both sides. It's going to be x minus 3 is equal to 2 cosine of t. And then we have the y plus 1 is equal to 3 sine of t. We're going to go ahead and divide both sides by 2 here, and we're going to divide both sides by 3 here, and so we're going to get x minus 3 over 2 equals cosine of t, and then we're going to get y plus 1 over 3 equals sine of t. And then we're going to square both sides of the equation and add them together. So here is one where you do not take the inverse cosine to solve it for t. You do not take the inverse sine to solve it for t. All you simply do is square both sides and add them together. So we're going to do that. All right, we're going to square this. We're going to square that, square this, square that. And when you add both equations together, you are going to get x minus 3 over 2 squared plus y plus 1 over 3 squared equals, now notice, you're going to get cosine squared plus sine squared on the right-hand side, but we know from trig that is just 1. All right, so now this is looking kind of like an ellipse, but we're going to square it out. So it's going to be x minus 3 quantity squared over 4 plus y plus 1 quantity squared over 9 equals 1. And now we can identify the shape. This is going to be an ellipse. So let me write that up here. This is going to be an ellipse centered at 3, -1, and it has looks like an x radius of 2 and a y radius of 9, and so, x radius of 2 and a y radius of 3, because those are the square roots of these numbers right here. All right, now we're getting into some actual calculus problems, and we are going to find the derivative of a parametric equation. And so we can see here in the green that the dy dx is equal to dy dt divided by dx dt. All right, this is true because when you divide fractions, so let's just say dy dt, when you divide fractions you multiply by the reciprocal of the denominator, so that's going to be multiplying by dt dx. And you can see here that when you do that, the dt's are going to cancel, and that just gives you dy dx. So I'm going to erase that so you have a little bit more room. And we're going to do that. So we're going to take the derivative of the y function with respect to t. So dy dt is going to be 6t minus 2. And then dx dt is going to be, well, looks like it's going to be t to the -1/2. All right, when you take the derivative that's what you get. And now we're going to divide those, and so dy dx is going to be dy dt, which is 6t minus 2, over t to the negative 1/2. And of course we know that we can move that up to the top. So we're going to move this guy up there, and that's going to give us t, so we'll just say that equals t to the 1/2 times 6t minus 2. And then you're going to distribute the t to the 1/2 in there, and your final answer is going to be 6t to the 3/2 minus 2t to the 1/2 power. And that is your dy dx for parametrics. All right, now we're going to work on the second derivative, and there's something that you really need to pay attention here for the second derivative, and that is the fact that when you take the second derivative, all you're doing is you are taking the derivative of the first derivative with respect to t, and then you're dividing by dx dt. You are not taking the derivative of dx dt again. You're just simply taking the derivative of the first derivative with respect to t and dividing by dx dt. So let's go ahead and do that. So the derivative of dy dx with respect to t is going to be, well, we got to take the derivative of this function, so that's going to be 3/2 times 6, which is going to be 9t to the 1/2 power. All right, and then minus, and we're going to take the derivative of 2t to the 1/2, which is simply going to be t to the negative 1/2. And then we're going to divide that by dx dt again. And dx dt, once again, was just t to the negative 1/2. And so we're going to move that t to the negative 1/2 up to the top. And we are going to end up getting, once you bring it up there and distribute, it's going to be 9t minus 1. And that is the second derivative value. All right, we are back to finding tangent lines. So this is a great review of some semester 1 stuff. In order to write a tangent line, we're going to use the point slope formula, which we remember is y minus y1 equals m times x minus x1. So we need a point, and we need, so that's the first thing we need, and we need the slope at that point. So it tells us that we want to do this when time is equal to 3 pi over 4. So we're going to take that t and we're going to plug that in to y, and we're going to plug it in to x to get our point. All right, so 3 pi over 4, the cosine of that is going to be negative root 2 over 2 because it's in the second quadrant. And so the x coordinate is simply going to be 4 times negative root 2 over 2. So that's just going to be negative 2 root 2. So that's my x. And my y is going to be y equals 3 sine of 3 pi over 4, which is going to be root 2 over 2 again. So the y is going to be 3 root 2 over 2. All right? And so now we got our point, and now we need the slope. So we need dy dx. So we are going to do, so we will remember that dy dx is equal to dy dt over dx dt. And so dy dt is simply going to be 3 cosine of t. And the bottom is going to be dx dt, which is going to be negative 4 sine of t. And we recognize that cosine over sine is simply cotangent. So this is going to be negative 3/4 cotangent of t. So maybe I'll put that right there. So cotangent of t. All right, so now we're going to plug in our 3 pi over 4 into our derivative, and we will see that the cotangent of 3 pi over 4, well, let's just kind of review a little trig here. 3 pi over 4 is in the second quadrant, and so it has sides of -1, 1, and √2. And so the cotangent is adjacent over the opposite. So that's just going to be -1. And so -1 times -3/4 is going to give us 3/4 as our slope. And so then we're going to do y minus the y-coordinate, which is 3√2 over 2, equals the slope, 3/4, times x minus a minus 2√2, so that's going to be x plus 2√2. And because this is calculus, we're going to leave our answer in point-slope form, and so that is our answer. All right, in this next example, we're going to find all the points on this parametric curve where there will be horizontal and vertical tangent lines. And so let's just say, just so we can understand this, let's just say you have some curve that looks like this. That's probably not the best curve, but a horizontal tangent line would be when dy dt equals 0. Or let me say it this way, the change in the y-coordinate as time is changing is equal to 0. And you can see that's just a flat line. The y is not changing, the x is changing. So that would be when there is a horizontal tangent. Now, if you're trying to find when there's a vertical tangent, you could probably figure this out. Vertical tangent would be when dx dt equals 0. In other words, where on the curve is the x-coordinate not changing at all, but the y is. All right, and time is also changing. So that's what we want to do whenever you're asked to find these points of horizontal and vertical tangency. So we're going to start with dy dt, and we are going to take the derivative of that. So dy dt is going to equal 2t minus 3. And so we are going to set that equal to 0, and we get t equals 3/2. And dx dt is simply going to be 2t plus 1. Set that equal to 0, and you get t is equal to -1/2. And for the sake of time, I'm going to save us the mundane algebra, actually not even algebra, arithmetic. If you plug those time values back into the x and y parametric equations, well, for dx dt, we will get, so let's just say when t is -1/2, what you will get is a ordered pair of -1/4 for your x and 27/4 for your y. Okay, so we'll call this the vertical tangent. Vertical tangent. All right, and so then we will now plug in 3/2 in for t into both equations. So when you do that, you are going to get another ordered pair, and that's going to be 15/4 for your x and 11/4 for your y. And I would encourage you to work those out on your own. Make sure that you know how to do all the fraction work to get those answers. All right, in this last example, we are going to talk about how to find arc length for parametric equations. We recently studied arc length in Chapter 7 when we did area and volume, rotation and whatnot. And now we're going to do arc length for parametric curves. So the formula is kind of similar. except instead of having 1 plus f prime of x squared underneath the square root, you've got this dx dt squared plus dy dt squared. And so we're just going to plug it in. Notice the problem says set up the integral, but do not evaluate. So pay attention to things like that. So we're going to find dx dt first. So dx dt is simply going to be 2t. And dy dt is going to be 12t squared. 12t squared. All right? So we're going to plug those in and set up our integral. So our integral is going to go from 0 to 1, big square root, dx dt squared is going to be 4t squared, plus dy dt is going to be 144 t to the fourth dt. And we want to make it look a little nicer, so we can factor out from there a 4t squared. So let's just say that'll be from 0 to 1, and we're going to factor out a 4t squared, and that's going to give us 1 plus 36t squared. Move that over there, and dt. And then we recognize that this is a perfect square, so the square root of that is simply 2t. And so our final answer should be the integral from 0 to 1, and we'll call this s for arc length, is equal to 2t times the square root of 1 plus 36t squared dt. And that is arc length. Pretty simple concept. All right, we'll do some more problems in class tomorrow.